All right, let's get started. Welcome everybody to the third lecture of CS294-112. Today, for most of today's lecture, we're actually going to have a tutorial on TensorFlow and deep neural networks from Greg Kahn, who's one of the GSIs in the class. But before we get to that, I want to wrap up some of the discussion from last week, since I didn't get to quite finish all of the theory at the end. So just as a reminder, at the end of last week, we talked about how, well, while imitation learning might be a very reasonable way to get policies in a lot of situations, there are some cases, of course, where imitation learning is not enough, which is why we have the rest of the class on reinforcement learning. And we talked about how if you want to go beyond imitation learning, it's really important to actually define what actually makes a decision good or bad. So instead of just saying that what you want to do is match the actions that were taken in the data, you might want to formulate some kind of objective function, which in reinforcement learning we call a reward function or a cost function. So the example I used on Friday was that, well, if you're in this situation where you have the example with the tiger and you need to take some action, maybe without even worrying about what the policy is or how it's represented, you can just define what makes a good decision or a bad decision in terms of something that you actually care about happening in the world, so, or not happening, as the case might be. So maybe if I really don't want to be eaten by the tiger, my objective is to minimize the log probability that I'll be eaten by the tiger, conditioned on what I actually do in the world. And in general, in decision-making problems, you can write down a cost function or a reward function that tells you how much you prefer certain states or certain actions, and then you want to maximize, if it's a reward function, or minimize, if it's a cost function, this quantity over all time. So I want to minimize the probability that I'll be eaten by the tiger, not just right now, but at any point in the future. So even if I don't run away from the tiger right away, maybe the tiger won't eat me until a few seconds into the future, so I really need to look ahead to figure out how to do this. And that's what we'll cover basically in the rest of the course, how to solve these kinds of problems. But then we had a little digression where we talked about, well, we talked about this, but we also talked about whether this notion of a cost function or a reward function does actually still extend to imitation. Because with imitation, it was, we kind of described the procedure for doing imitation learning, but it was a little bit unclear as to what the actual objective of it is. So having introduced the notion of cost functions and reward functions, we can actually go back to the world of imitation learning and actually write down a reward function or a cost function that imitation learning is optimizing. So one very simple example, there are a few choices here, but one very reasonable choice to say, well, your reward function in imitation learning is just the log likelihood of taking the action in that state that the expert would have taken. So here, pi star is a deterministic function. It's an unknown deterministic function. That's basically the expert's decision-making process, the unknown decision-making process of the human. And your goal is to maximize the log probability of taking whichever action the expert would have taken. The important thing about this kind of objective is that this is not saying match the actions that were actually in the data. This is saying match the actions that would have been taken at the states that you actually visit. So if you find yourself in some state where you never saw any data, you still have this as your objective. So you might still fail to take the right action at the states that you visit, even though you're succeeding at taking the right actions at the states that the expert visited. And that's, of course, coming down to that whole distribution mismatch thing that we covered last week. We also introduced a slightly simpler objective. Here I'm writing it as a cost function, but you can also write it as a reward function, just negate everything, which is the 0-1 loss. The reason that I introduced the 0-1 loss as opposed to this log likelihood is because it's a little easier to analyze bounds in terms of the 0-1 loss. You can do all the same bounds using the log likelihood loss. It's just easier to do with the 0-1 loss. So the 0-1 loss just says your cost is 0 if you match the expert and 1 if you didn't. So you basically pay a price of 1 for every mistake. Just a little bit simpler, makes the analysis more straightforward. Okay, and then we did a little bit of analysis in this little simple kind of tightrope walker domain where we said, okay, we're going to have our 0-1 loss, and then we're going to make some assumption. You need to make some assumption if you want to bound your cost. So the assumption here is a very, very simple assumption. It says, for all the states in your training set, your probability of making a mistake is bounded by epsilon. That's a very reasonable assumption, because if you trained on those states, assuming that you got low training error, you're going to be able to bound your probability of a mistake. So this is basically saying, I have a good enough model, I have a good enough learning algorithm, so that at least the training error is low. So the tightrope walker domain just to remind you, we said, okay, it's a very simple domain, it's discrete, and you have a sequence of states here in the middle, which are like the good states, and your demonstrations will always walk to the right along the rope, and they will never fall into these red regions. And once you fall into those red regions, you can never get back up. But this is a very funny tightrope walker. He doesn't actually care about falling. What he cares about is making mistakes. So the only reason that he's unhappy when he falls into these red states is because he doesn't know what to do there. So he keeps making mistakes. And then what we said is, well, okay, based on this assumption, can we bound how much cost we'll get in the tightrope walker domain? Can we bound the quantity that we really care about, which is the total cost over all time? So let's say that the episode is capital T time steps in length. We have a probability of epsilon of making a mistake on all the states that we saw during training, which are these gray states. On states that we didn't see during training, all bets are off. So pessimistically, we can just assume that if we enter some state that we didn't see during training, we'll definitely make a mistake, because we can't bound that probability. So then we said, well, what's the probability of making a mistake in this first state? Well, that's just epsilon. And if you make a mistake in that first state with probability epsilon, you fall into one of these red states, and of course you have capital T time steps left to go, so then you'll keep making mistakes for capital T time steps, because in these red states you always make mistakes. So on the very first time step, with probability epsilon, you'll incur a total cost of capital T. With probability of 1 minus epsilon, you keep going. And then over here, you again have a probability of epsilon of making a mistake, falling into one of the red states, and then getting capital T minus 1 cost, because you then make mistakes for all the remaining time. So basically, what this comes down to is that you have a sum of these terms. All of these terms have a multiplier of capital T, and there are capital T of these terms. So capital T terms, each of magnitude capital T, that means that your total cost is on the order of T squared. And they're all multiplied by epsilon on the left. So capital T terms, each of the order of epsilon T, which means that your total cost is bounded by epsilon T squared. And this is basically the best bound that you can have unless you make some additional assumptions. So if you have this possibility for distributional mismatch, epsilon capital T squared is the bound you're going to get on your cost, which is very bad, because that means that the longer your task gets, your cost basically increases super linearly. So for a long enough task, even for very small epsilon, even for a very powerful neural network, you might incur very large cost. But this analysis is a little bit simplistic. So this analysis deals with a situation where you're only bounding your error on literally the states in your training set, which is not even making use of any kind of supervised learning generalization result. So the part where we left off on Friday was we said, well, okay, let's think of a more general analysis. Let's say that you have, for example, image observations. When you have image observations, you never really see the same exact state twice. So assuming that your error is only bounded on states that were literally in your training set is not very interesting, because you would never see the same state twice. You might see slightly different images. So instead, what we can make is an assumption that's a little more standard in machine learning, which is we say, well, we have bounded generalization error, meaning that if you see new states from the same distribution as your training set, then your error is bounded by epsilon. And this is very reasonable. It's just a standard assumption for supervised learning. And for simple function approximators, you can show that generalization error is bounded given a big enough training set and all that other stuff. So this is a reasonable thing to assume in most cases. Then we talked a little bit about how with Dagger, if Dagger sort of succeeds at doing what it's supposed to do, and the training distribution approaches p theta s, the distribution of states that you see from your policy, meaning the distribution mismatch problem goes away, then you can bound your cost by epsilon times capital T, because if p train is equal to p theta s, then your probability of making a mistake is always epsilon. You always have capital T time steps, so the very best you can possibly ever do is epsilon times T. So that's the best bound on a cost you can ever have, and that is indeed what Dagger gets when it eliminates the distributional shift. So that's all good. And then the interesting analysis, which is what I'm going to do today, is for the case when p train is not equal to p theta s. So this analysis is meant for us to understand why we actually need to worry about Dagger. Like, why should we do Dagger? Well, because if p train is not equal to p theta s, we're going to see that we get a much worse bound. And that's what we're going to go through today. The algebra here is going to be a little more involved, because now we have to deal with distributions. But I wanted to go through it because the kind of analysis we do here is actually just generally it has a lot of useful techniques for analyzing distributions in sequential decision-making processes, and the same kinds of concepts will also come up in other reinforcement learning topics. So I wanted to go through it here for imitation learning because it's actually pretty simple, but the basic concepts will come up later on as well. So when we analyze the case where the training distribution is not equal to the p theta s, this analysis, by the way, is going to follow the analysis in the Dagger paper, this is the title of that paper. It's a little long, so I have it on the slide. The first thing we're going to do is we're going to introduce an interesting little identity. And this identity allows us to relate one state distribution to another. So let me explain what this equation is saying. This is looking at p theta st, meaning the distribution of states at a particular time step t. So maybe the distribution of states 10 seconds after the tightrope walker starts walking. And we can actually write an equation for this distribution as following. We can say, with probability 1 minus epsilon to the power t, you do not make any mistakes up until time step t. So at time step 1, your probability of making a mistake is epsilon, which means your probability of not making a mistake is 1 minus epsilon. If you don't make a mistake on time step 1, then on time step 2, your state distribution is the same as the experts because you didn't make a mistake. So that means that the probability of not making mistakes 2 times in a row is 1 minus epsilon squared, and then at time step 3, you're in the same state distribution as the expert. So in general, after t time steps, you have 1 minus epsilon to the power t probability of not making a mistake, and if you didn't make a single mistake, then you're in the same state distribution as the expert. Now, there is also the opposite, which is 1 minus epsilon to the power t. That's the probability that you've made at least one mistake. You might have made more than one, but this is the probability that you made at least one mistake. And you can construct pathological decision-making problems like the tightrope walker, where if you make even a single mistake, you'll be in a totally different state distribution from the expert. So we can call that distribution p mistake. This might be a really complicated distribution, but this is basically the distribution that you get if you made at least one mistake. And we know from the tightrope walker example that we can construct pathological situations where if you make even a single mistake, this p mistake will be totally different from p train. So we can always write down an equation like this for any distribution. And we're basically not going to make any assumptions about p mistake. We're just going to say, OK, p mistake can be arbitrarily bad. But p train, I know about p train. That's where I can bound my error. So this is the probability you make no mistakes. And this is just some other potentially very bad distribution. So now we can start relating p theta st to p train st. And we're going to relate them to each other in terms of what's called total variation divergence. Total variation divergence is just a funny way of saying take the absolute value of the difference between two probabilities and then sum those absolute values up over all the states. So when you see this kind of norm, what that's saying is just subtract p theta st minus p train of st and take the absolute value. OK, so because we can substitute this equation for p theta st, what are we going to get? Well, we're going to get one term which is p train times 1 minus epsilon to the power t minus p train. But the p trains cancel because they're always equal to each other. So that term just goes to 0. And then we just have this remaining term, which is 1 minus epsilon to the t times p mistake. That term doesn't vanish because p mistake is not equal to p train. So we can write this, that the total variation divergence between p theta st and p train st is 1 minus epsilon to the power t times the total variation divergence between p mistake and p train. OK, so this relationship is a little bit non-trivial. Does anybody have any questions about this? OK. So now remember that we can't make any assumptions about p mistake. In fact, p mistake, we can construct pathological cases where it's as different from p train as possible. So can anyone tell me what's the largest possible total variation divergence that you can have between two probability distributions over discrete variables? So I hear 1 a few times. OK, so probability distributions have to sum to 1. So the largest value they can possibly have in any state is 1. And they have to be greater than 0. So let's say that we have the worst possible setting, like p mistake is 1.0 in state 0, and p train is 1.0 in state 1. What's the total variation divergence between these? What's the sum of absolute value differences? 2, exactly. So the biggest total variation divergence we can possibly have is 2. So we can bound this by 2 times 1 minus 1 minus epsilon to the power t. So that's the largest possible difference we can have. We could stop right there. We could say this is our bound. We can simplify it a little bit, however, by using a neat little algebraic identity. This is just basically a fact in algebra that for any value epsilon between 0 and 1, 1 minus epsilon to the power t is greater than or equal to 1 minus epsilon times t. So this is just like from an algebra textbook, basically. And you can subtract 1 from both sides, take the negative, and that lets you bound this by 2 times epsilon to the t. So it's just it's a shorter, more convenient expression. Yes?
Can you explain again why it became 2? Like, they should be at the same time. You said, like, at time, you compared to time, state at time 0?
But there are many possible states. So let's say you have like 3 states in the world, right? So this is a distribution over 3 values, this is a distribution over 3 values. And let's say this one is 1.0 in state 0, and this one is 1.0 in state... Yeah, this is a sum over all the states. That's right. Okay, so now we have a bound on the difference between the 2 distributions, and the bound looks very simple. It's just 2 times epsilon times t. So now let's analyze the quantity that we actually care about, which is the expected cost. And here all I did is I took the sum and I took it out of the expectation by linearity of expectation. So it's a sum over the time steps of the expected cost. So this thing, exactly the same as this thing. All right? So let's write out just the definition of expectation. That's just the sum over all states of p theta st times ct st. That's just definition of expectation. And now we're going to do a little substitution to basically put in something like what we've seen here. So how do we do the substitution? Well, we're going to say p train is equal to, p theta is equal to p theta plus p train minus p train, right? You can always add p train minus p train because that adds up to 0. So you would get p train, you get p theta plus p train minus p train. P theta minus p train is bounded by p theta minus p train absolute value because, obviously absolute value is going to make the negatives positive, so it's going to only get bigger. So you can always put the absolute value in there. And then after you do that, then you get this term times CT, and you get this term times CT, right? C max, the largest possible cost, is always larger than CT, so we can always replace CT with C max. So this is a valid bound. Does anybody have any questions about that? Okay. Can anybody tell me what the largest cost at a particular time step for a particular state can possibly be? What is C max?
1.
1, exactly. That's just from the definition of my cost. It's 1 if you make a mistake and 0 otherwise, so the largest cost is 1. So I can just ignore this term, it's 1.0. So now I've bounded my expected cost by p train times CT plus this quantity which I've bounded up here times 1. What is the expected cost under p train? Yes? 0? It's a little bigger than that. Yes? Epsilon. Well, for a single time step, it's epsilon. But over all time, it's epsilon times t. Yeah, that's just because of this generalization bound. So this term, for any single time step, is going to be epsilon, and we're summing it over time steps, so it's epsilon times t. So this term is the good term. This one doesn't hurt us. But this term, this is going to be the nasty term. So we're going to have a sum over t of epsilon plus this thing, which is bounded by 2 times epsilon t. So it's a sum over t of epsilon plus 2 times epsilon t. And this, of course, is going to be on the order of capital T squared. So we have an easy term, which we don't care about, and a difficult term, which is on the order of epsilon t squared. So now we can see that in the more general case where you're dealing with probability distributions, your bound is still epsilon t squared. In fact, you can show that this bound is as good as it gets. So that's a little more involved to show, but you can look at this paper for the details on that. So that's basically showing that in the general case, if you don't match the distributions, you might get still quadratic cost. Okay, that's the more general analysis. A few notes about cost and reward functions. So far, we talked about this kind of nice theory. We have simple costs. Everything is very easy to analyze. When we talk about reinforcement learning, starting on Friday, things are going to get a bit more complicated in regard to reward functions, especially in practice. So you might think that you can get away with very simple reward functions, like a reward function that just says like 1 if you did your task right and 0 otherwise. -1 if you made a mistake, and 0 otherwise. In practice, for reinforcement learning problems, we often have much more complex cost and reward functions. So if you want a little robotic arm to pick up an object and move it to a target location, you think you can give it a reward of 1 for getting to the right place and 0 otherwise. But in practice, that's actually a very difficult reinforcement learning problem to solve. So if you look at kind of maybe open source implementations of common reinforcement learning algorithms and common environments, and you look at the reward functions, you might see something really complicated. Instead of something like what you would expect, which is 1 if you get it to the right place and 0 otherwise, you might see some complicated mess of terms that says, okay, there's some term that rewards you for getting close to the object, some term that rewards you for getting the object close to the location, some term that rewards you for minimizing how much you're moving the arm, and so on. And part of the reason why we often end up with fairly complex reward functions is that these very simple reward functions pose a very large exploration problem. It's hard for reinforcement learning algorithms to discover successful strategies even once so that they can begin improving. And we'll talk about exploration later on in the course too. Question?
In the previous slide, I think the summary should be that p theta minus p train should be 0 or close to 0 with dagger to be able to get the epsilon t. But does that mean that epsilon has to go to 0?
Well, not necessarily, because remember that, so the question was, if you want p train to be close to p theta, doesn't that mean that epsilon needs to go to 0? The reason it doesn't with dagger is that dagger doesn't actually try to change p theta, it tries to change p train by adding more data from p theta. So if you could get epsilon to go to 0, then you would also match the distributions, but with dagger you don't have to do that. Okay, so yeah, in practice, reward functions can be much more complicated if you're doing RL. Another example, walking. This is actually from the standard kind of benchmark walking task. Again, you'd think that your reward would be like 1 if you're walking and 0 otherwise, but in practice, your reward function is some complicated combination of terms, something for moving forward, something for like keeping the torso upright, something for not falling, all this other stuff. And in practice, we do that because exploration can be really difficult. Okay, so we'll learn a lot more about reward functions in the coming weeks when we talk about RL. And now I'm going to give the floor to Greg, who's going to give us a tutorial on TensorFlow and deep neural networks. Do you have HDMI?
I have the converter thing that they left. Yeah, that one.
DisplayPort?
DisplayPort, yeah. Cool. Okay, hi everyone. My name is Greg. I'm one of your GSIs. So today I'll be talking about TensorFlow overview. So for this lecture, we're going to assume that everyone is familiar with machine learning and you've probably seen neural nets before, you know, concepts like backpropagation, but we're going to cover a bit of it and then kind of walk through an IPython notebook with kind of the, I guess, the smallest set of things you need to know in TensorFlow to be able to just get started. So first, before we dive into, you know, TensorFlow, kind of what is the goal of this course? So the goal of the course is to train an agent to perform useful tasks. The goal of the course is not to learn how to train neural nets. That's just a means to an end. So we want to train an agent. So what is this going to involve? Well, we're going to have an agent, and it's going to be taking actions, and we're also going to have a data set. And we're going to be using our data set to train a model that our agent uses. So for example, in homework 1, you're training a policy that imitates an expert. So your model is some behavioral cloning. But then also in reinforcement learning, you're going to have the agent actually take actions in the world. It's going to get more data added to it and train your model and kind of do this loop again and again. So what we're going to talk about in this lecture is purely just how to train the model. So far what Sergey has talked about has kind of assumed that you can do that. Now we're going to actually talk about how to train models. So what is training a model? Well, this is, I guess, the field of machine learning. And I guess this is the field of machine learning on one slide. What is it trying to do? So in general, you're trying to learn a function f theta, which takes as input x and is trying to output some y. And then you train this model f theta of x to match some ground truth labels y. For example, if you were doing a classification task, maybe x would be images, and y would be, is there a cat, is there a dog, or some other animal. And now in order to train this, we're going to have some data set D, which has all of these training inputs and training outputs. And for all of them, we want to find the parameters theta such that we find the best model fit. So in general, what we're going to do to make this math concrete is the f theta is going to be a neural network. And the argument of theta, how do we find the parameters of the neural network, will be doing gradient descent. OK, so now we want to do gradient descent with neural networks. How are we actually going to code this up? So for this, we're going to use a library called TensorFlow. TensorFlow was developed by Google. And basically, it does two things. One, it lets you define computation graphs. Now, what is a computation graph? It's just basically you code up math, A plus B, addition, all this stuff. And then once you define your series of computations, you can say, OK, give me the gradient of this parameter with respect to this, which we'll need for gradient descent. And TensorFlow does all of this for you. For example, if you maybe took an undergrad course in machine learning, you might have had to manually do backpropagation or something like that. TensorFlow will do all of the hard stuff for you. OK, so TensorFlow. So there's two things. So first is defining the computation graph. So let's say I want to make this neural network. It has an input layer, it has two hidden layers, and it has some output layer, all with connections. So how would you define this? So you would first say, OK, the hidden layer 1 is some weight matrix W1 times x, and you pass it through some nonlinearity. Now that you have hidden layer 1, you can do the exact same thing for hidden layer 2. You take in the hidden layer 1, multiply it by weight matrix W2, pass it through nonlinearity, and now you get H2. And lastly, you can do it for the output y. So in your code, your first thing you do is you're going to define this, basically this computation in one direction. And now you want to actually train these model parameters. So what are the model parameters here? They're going to be W3, W2, and W1. These are unknown parameters that you need to optimize. So to do this, you're going to want to calculate gradients, so you can do gradient descent. So you calculate dy dw3, which should tell you how should I change my weights W3 in order to change my output y. And then you can go back through the computation graph and do this for each of the variables, each of the model weights that you actually want to learn. And this is the backpropagation algorithm. Well, I'm not going to go through the backpropagation algorithm. That could be a lecture in of itself. But if you want materials for it, you can Google for CS189 or just post on Piazza, and we can show that to you. But the nice thing is that all you have to define is the easy part, which is just the computations going forward. And TensorFlow will basically do everything for you, and you don't have to worry about this aspect, at least on this level of detail. Are there any questions, high-level questions about this? OK, cool. So before we jump into actually the code, TensorFlow is not the only library. There's a bunch of them out there. So there's no particular reason that we're using TensorFlow, except that it's just a commonly used one. So yeah, if you're familiar with any of these other ones, it shouldn't be too hard to pick it up. And if this is your first time using a deep learning library, then learning these other ones will be a lot easier after you've learned one. It's the same as a programming language. OK, so now we're going to switch to the notebook and walk through some concrete examples. OK, let me clear the output. Cool. OK, so in this tutorial, we're going to cover 6 things. So kind of what is TensorFlow on a high level? How do you input data for TensorFlow to use? How do you perform computations? How do you create variables, which you'll need in order to optimize? And then we're going to kind of combine all those into a short regression problem, so training a neural net to go from one input to one output, and then kind of miscellaneous tips and tricks. This is definitely not exhaustive. There's way more to TensorFlow. There's supposed to kind of be the core knowledge. Okay, so first we're going to input or just run some useful functions that we'll be using. Let's see if we can read this. Okay, so TensorFlow is just a high-level way of defining a computation graph. So what does this basically involve? So first, you create a session. And what a session is, you can think of it as a blank piece of paper. It's where you write math on. So every time you start, you create a session. And then what you're going to do is first you're going to define inputs. In this example, I've created two inputs that are just constants. So A and B are both tensors. That's what we call kind of resulting outputs in TensorFlow. So they're both tensors. One of them is a constant of 1. The other is a constant of 2.0. And then using these inputs, we're going to do some operations. So right now I just did addition, super simple. And once you're done defining all your computations, at the very end, you can call session.run on one of the computations that you created. So saying session.run of C is kind of forcing the data to flow through the graph that you created. So it's going to start all the way at A and B. It's going to go through to produce C, and then it's going to give it to you as an output. And so we can see that when we actually run this, voila, it gives you C as a 3.0, since it's 1 plus 2. So now we're going to kind of go through each of these sections and show that you can do more non-trivial things that will eventually let us be able to train a neural network. OK, so the first thing we're going to talk about is how to actually input data. So in the first example, which I've repeated here, is you would input your data using just constants. So if you do this, you'll get the computation that you want to do, which is getting 3.0. But this isn't very useful. I mean, that would suck. Basically, every time you got a new data set, you would need to create a constant, and it would not be very flexible. So what we can do instead is have inputs in which you get to feed data in at runtime. So this is the same example, except instead for A and B, I've added this thing called a placeholder. So for a placeholder, what you need to tell it is you need to say, what type are you? So I said, OK, you are a float 32. You need to say what shape it is. I'm going to say this is a one-dimensional input. And you can give it a name to make it more recognizable. So right now, I've done that for A and B. I can do the same exact operations that we did before. So I can do addition. But now what changes is at runtime, you need to feed in what A and B are going to be. So in this example, I can again do feed in 1 and 2. And then it'll produce what is C, what is the addition operation when I pass a 1 or 2. But the nice thing is I don't need to recreate the graph if I want to pass in a different input. So if I want to add two different numbers, 2 and 4, I can just call a different session.run and get the appropriate output. So if you go ahead and run this, you'll see that C0 and C1 do end up being 3 and 6, because it's just addition. OK, so that's how you can feed in data input. But one issue with this is that you can only feed in a fixed size. So for example, this graph can only deal with inputs of shape 1. And this is not ideal. So when we're doing training with machine learning, we often want to pass in batches of data. And we might want to change how many data inputs we want to put in. So what TensorFlow will let you do is it'll let you actually input a variable number of inputs. So how do we do that? We take the same exact example that we had before, but we just change that shape of 1 to shape of none. So what the shape of none means is, OK, I don't know what it's going to be, what the size of that variable, of that placeholder is at when I create the graph, but I'll let it figure it out when I actually call session.run. So what you do is you do the same thing. You create the placeholder, but with shape nones. You do the same operations. But now when you pass in the data at runtime, I can do, like I did before, just a one-dimensional input, 1.0 and 2.0. But I can also now pass in a different shape. So these are two-dimensional vectors, 1.0 and 2.0, and 2.0 and 4.0. So now what happens when I run this graph? So what we'll see is that both the A placeholder and the B placeholder, they have unknown shape. So that's why there's going to be a question mark. So that's what happens if you just print out the raw tensor. Now, what actually happens at the output? Well, C0 was just 1 plus 2, so that's why you get 3. But the second computation was adding 2 vectors. So when you add these 2 vectors, you get 3, and you get 6. So this is how you can input variable length data. Now, one thing I do want to mention is that this shape, none, you can only have one of your dimensions be none. So in general, doing something like this, most operations don't generally play well with that, basically because they need to know like how big should the matrix multiplication be at runtime. So in general, you're going to have this none be the first dimension, and it'll be your batch size. That's the most typical use case. There are other weird examples, but that's the most typical. OK, so that's about how to input data. Any questions about how to input data? OK. Cool. So now let's go on to how to perform computations. So right now, all of our examples have just been doing addition, but we can clearly do more advanced computations than just adding things together. So first, let's create some data. So I'm just going to create some constants just for simplicity. So I'm going to create A, which is just a vector, -1, -2, -3, and then B is just going to be a horizontal vector of 1, 2, 3. So this is going to be our running example for this section. So again, we can do addition operations. So if I take B plus B, well, B is 1, 2, 3, so B plus B is 2, 4, 6. OK, easy peasy. But now let's say I do something like A plus B. So if we remember, A was this vertical vector, B was this horizontal vector. Now what's going to happen? So it actually gives you this kind of weird output. You would think that because they're both kind of 3-dimensional vectors, it would just add them together. But instead, we got this 3x3 matrix as output. So what happened? So what happened is that TensorFlow tries to do this thing called broadcasting. So it tries to match dimensions. And in this case, what it ended up doing is it ended up duplicating A multiple times and basically turning both of these into 3x3 matrices and adding that together so that the dimensions would match. So you should be very careful when you're doing computations. Some things might work when they shouldn't work, or when you think they shouldn't work, but they'll just go ahead and run. So be very, very careful. And as you're going through, kind of look at your tensors, look at the shape, and make sure that everything matches. Sometimes it is useful, though, so you might want to do this on purpose. But just make sure it's intentional, not accidental. Another way that things can be different than you expect is, first you might do A times B, and you might think that that might be some operation, like maybe matrix multiply, if you're kind of familiar with MATLAB. But in fact, it's actually element-wise. So if you wanted to do matrix multiplication, you would need to use TensorFlow's matrix matmul function. And you can see the difference here. So if you take A and B and you do element-wise multiplication, it's going to do that same broadcasting thing and then multiply them element-wise. Well, if you do matrix multiplication of B times A, well, it's just the dot product, so you'll get the sum of multiplying together, which is -14. So yeah, be careful about overloading, and definitely look at what TensorFlow, it gives you default gives you operations to use, and those are kind of the safer way to use things if you're ever unsure. Next, operations can be chained together. This one's kind of obvious. If I do B plus B and I get some output, then I can do some other operation and then keep going. So this just shows, B plus B, 1, 2, 3 gets 2, 4, 6. You add 1 to it, you'll get 3, 5, 7. And this is kind of the basis of how you're going to create the neural net. You're going to apply layer again, and again, so everything will actually work out. And lastly, TensorFlow has built-in operations. For example, if you want the mean of some vector B, you can just use TF reduce mean. So 1, 2, 3 will reduce to the mean of 2.0. And there'll be a bunch of different functions like this that are useful. And you should go look through the TensorFlow API online. It's not actually that big, so it's worth spending 15 to 20 minutes just to see kind of what tools they give you, since you don't want to reinvent the wheel when you're doing your homeworks. Are there any questions about how to do computations? Anything? It's okay if it seems stupid in your head. Now's the time. Yeah?
Can you mix TensorFlow computations with like regular Python computations when you're inside the graph?
So I guess two answers. One, I guess regular Python operations like using this plus operator, you can because TensorFlow has made their API work with it. But you cannot take, well, and another example is, this Python, this is a Python 1. It's not a TensorFlow 1, but TensorFlow knows what to do with it. So there is some default mixing that it allows. But for example, you can't take a TensorFlow tensor and a NumPy array and add them together. That just won't work. If you do want to get constants and stuff in, you can use tf.constant, but in general, yeah, not necessarily.
Can you give an example of broadcasting actually help you?
Broadcasting helping. Actually, here, this C0 plus 1, for example, because, let's see.
Yeah, I mean, that's adding a constant. That's not adding to arrays.
Right, but it is doing broadcasting.
Yeah, I know.
Okay, but you want the kind of multi-dimensional broadcasting.
Yeah, because I found it's really annoying. I don't know why it's implemented in that way.
For example, let's say you have a batch of data and you want to only train on, I don't know, sorry, I'm trying to think of a non-trivial example. Broadcasting. Or okay, let's say you're doing classification and you're trying to classify dogs and cats. I don't know if anyone can see this. So maybe this is your output vector y, and you want to match it. So basically, let's say this is cat, and this is dog. And maybe your data looks like this. So you have, well, 2 dogs and 2 cats. These are one hot vectors, so these are your labels. Now let's say you're going to form your classification loss, but you really, really, really want to classify cats correctly. So I might say, okay, when I'm doing my loss, f theta of x, instead of doing it minus y, I want to have it weight them differently. So what you could do is you can form the same loss function and weight them differently. So maybe I want to, sorry, this is hard to read. Maybe I want to care about the cats 90% at 90% level and the dogs at 10% level. I can just literally write 0.9 comma 0.1 as and multiply it by y, which is this tensor, and it'll broadcast it so that it multiplies each of them by 0.9, 0.9, 0.9, 0.9, and 0.1, 0.1, 0.1, 0.1. So that's a way in which it kind of broadcasted across the whole batch, even though you just wrote just 0.9, 0.1. So that was a kind of specific example.
Another example that comes up in RL very often is if you want to standardize your inputs, like you want to subtract the mean, divide by the standard deviation.
Yeah, that's a good one. So yeah, and even in standard supervised learning, you want to make your data have a good range, subtract mean, divide by standard deviation. It'll automatically broadcast to the batch, which is convenient.
I think as of recently, the preferred input for TensorFlow is using the dataset part of the API. Is that useful, or is that premature optimization somehow purposes?
Premature optimization. So TensorFlow was created, I guess, more of in a standard supervised learning, machine learning paradigm where you have a fixed data set, you gathered it, and then you just train your model once. And for that, that's why they created these other ways of inputting data that is more efficient. But in RL, we have our data set, we train our model, then we get more data, and we have this loop. And for that, it's a little more non-trivial to use these optimized data inputs. So in general, do not pre-optimize. Yeah. Cool. OK, let's move on to the next part. So the next part is going to be how to create variables. So right now, everything has just been kind of constants that we've passed in and doing some fixed operations. But we're going to want to have variables so that we can have parameters that we can learn. So these are going to be the parameters of our neural net. So first, let's create some data. So right now, we'll just have one tensor, B, it'll just be 1, 2, 3. And now we're going to create a variable. So for this variable, we're going to give it a name. We'll just call it myvar. We'll give it a shape. Say it's a 1/3 tensor. What type is it? It's going to be a float. And you get to choose how it's initialized. So for this, I'm just going to say initialize to a constant value. And the constant value will be 246. So let's say I run this. If you actually print out what the tensor is, it gives you the same exact information: the name, the shape, and what type it is. So that's all you do to create a variable.
You have to initialize.
We'll get there.
Is there a reason, so if you move up, is there a reason you create two succession? Like you create a succession,
Oh.
make a constant, and then create another one?
That's a typo. Thank you.
Okay.
So yeah, we'll get to the variable initialization. So you create your variable, and what you can do is you can say, OK, create this variable, and TensorFlow has this nice way of keeping track of what variables you've created at all time. So it has this internal list, and you can see it added this one variable to it.
There are multiple ways to create variables.
Which one?
Why do you prefer like get variable? There's like tf.variable.
Yeah, tf.getVariable can play nice with this thing called reusing. So if you want to kind of call a computation graph multiple times but use the same variables. So I think in general, getVariables kind of has some safer built-in mechanisms. If that didn't make sense, don't worry. OK, so we have our variable that we created. We called it var. Now what can we do with it? So with this variable, we can actually do the same exact kind of computations we were doing before. So for example, I'll take this constant b that we created plus the variable, and that'll just go ahead and work. So you can see is that if we print out b was a constant of shape 1, 3 that we created. Variable had a shape 1, 3, also a float. And if we add them together, it'll give you a tensor that's also 1, 3. So all this is to say is that whatever we did before that we can do with tensors, you can do with the variables. In fact, a variable is a tensor. It's just treated slightly differently when you go to train your model. So now that we can do that, how do we actually use the variables at runtime? You do have to do one extra operation. You have to initialize your variables. So what you do is you say tf.gimme an initializer for your global variables. So what this will say is for everything in the global variables list, I want to initialize it. And this will give you an operation back. So once you have that operation, you just call ses.run on it, and now all your variables are initialized to their initial values that you passed in when you created them. So now that they're initialized, we can go ahead and call run and get our output of our computation graph. So if I call session.run on C, and to reminder, C was this constant b plus our variable, I will get 1, 2, 3, 2, 4, 6, and the addition is 3, 6, 9. So kind of all of this is just to show that there's no difference with variables. So far, they'll only be different when we go to actually train the model. Are there any questions about variables before we dive into kind of a regression problem? OK. So now the next thing we're going to do is how to train a neural network for a simple regression problem. So by simple regression problem, we're going to create some data. So the data that we're going to train is this sinusoid. So the inputs are going to be the x-axis, and the outputs are going to be the y-axis. And now here below, we have all this code, which is basically a one-stop shop for everything you'll need to do to train a neural net. So we're going to step through it one by one so you guys can get a sense for how everything actually works. OK, so first, we are going to create our session. Then we're going to create our model. So what we're going to do for creating our model is we're going to create our inputs. And for our inputs and our outputs. We need the inputs so that we can feed data in, and we need to be able to feed in the outputs so that we can train the model, since we need to do supervised learning. And for all of these, the shape is going to be none, 1 because it's a 1D input, just the x-axis, and it's going to be a 1D output. So this is why it's none, 1.
Why did you have to have the 1? Why can't you make it none?
You could also just do none, but this is just to make it clear that this is a one-dimensional problem. For example, if you were to do two-dimensional regression, you would put it 2. For example, in your homeworks for behavioral cloning, the inputs will be kind of the state of your Mujoko robot, which will, I don't know, 7, something like that. And the output will be how many actions could you take. So that's the number you'll be changing. Yeah, and keep yelling questions as I go through. Now next, what we're going to do is we're going to create our variables. So for our variables, we're going to do a neural network. So each layer will consist of a weight and a bias. And we're going to do 3 layers. So for all of these, the first layer, the input, it takes as input a shape of 1 because our data is 1D. And we're going to say go to a hidden size of 20. Now for layer 2, the previous layer was 20, and I'm going to say, OK, let's make the next layer 20 also. And then for the final layer, we want to go from the previous layer, which is also 20, to the output size of 1. So we have a 1, 20, 20, 21. And for all of these, we're going to also have biases, constants, that you add as well. Yes?
Do you use that where you set up explicitly the weights and the biases as opposed to just doing the layers and dense or con?
I'll get to that in the tips and tricks. So what I'm doing right now is kind of the lowest level usage of TensorFlow. There are higher level uses of TensorFlow. There are packages that are even higher, like Keras. So I guess this is might be viewed as primitive by some people, primitive use of TensorFlow. But like this is sufficient to get things working. OK, so now that we've created all of our variables, we're going to throw everything into a list and kind of create the neural network sequentially. So we're going to go W0, W1, W2. Then the biases will go B0, B1, B2. And now we need to choose what activations do we want. So remember that neural networks, each hidden layer is passed through a nonlinearity, and this is what gives the power, or the expressiveness of a neural net. So for all these, we're going to use a ReLU, which is a nonlinearity that is looks like this. It's like an elbow. We're going to use that on the first 2 layers. And on the last layer, we're not going to have any nonlinearity. This is because we want to predict a sinusoid. And a sinusoid can be positive or negative. So we're just going to let it be. So now that we have our weights, biases, and activations, we're going to actually use them. So we're going to iterate through each weight, bias, and activation together. So in the first, we would get W0, B0 in the ReLU. We would take the start layer will be our input. Now what we do is we take that layer, we do a matrix multiplication with the weight W, we add the bias B, and that'll give us kind of, we did matrix multiplication plus the bias. And if there is an activation function, like if it's a ReLU, then we'll apply this nonlinearity, this activation, to get the next layer, and we'll repeat. So after one loop, we'll have used W0, B0, and ReLU, and now on to the next iteration, where we'll then multiply by W1, then we'll add the bias B1, and then we'll apply the nonlinearity ReLU. Then we'll go to the last layer, do W2 matrix multiplication, then add B2, and not do any activation. And then that'll be the output prediction of our neural network. Are there any questions on this loop, actually creating the graph? Okay, so I put all of this into a function called create model. So create model will give you back the input placeholders and the output placeholders, so you can feed data in and out. And it also gives you the output prediction of the model. So these are the three things you need from
Is
it.
there any shortcut to just return all of the placeholders that you just created in the graph? Like, you don't have to explicitly just mention it?
Not that I know of. I usually keep dictionaries around, so it's easier just to index them, but yeah. Okay, so we've created our model, and now what we're going to do next is we want to create our loss function. So remember, in machine learning, we want to make our predicted output of our model match some ground truth label. So for this, we're going to just do a mean squared error. So we take our output prediction, and we want to make it similar to the ground truth output, which is this output placeholder. And it's an output placeholder so that you can feed the ground truth labels in. And we square them, and yeah, so when we square them, this gives us kind of our squared L2 loss. This is a common mean squared error function. And then we call reduce mean. So this part is important since the output pred minus the output placeholder is still over a batch because you're feeding in batches of data, but you want to compute the loss over the whole batch. So we're going to just do the average loss over the whole batch, and that's what this reduce mean will do. So now we've kind of boiled down our loss function to this is just one number, the mean squared error that we're going to want to minimize. Is there any questions about forming this loss function? Cool. So now that we have this loss function, we want to do gradient descent in order to minimize the parameters. So what we'll do is we'll create an optimizer. So in this case, I'm using this thing called the atom optimizer. You can view this as a stochastic gradient descent method. And then with that, we can call minimize this loss function. And what this will return is this will return an operation that will let us perform gradient descent, but it will do everything else under the hood. So notice that like we didn't calculate any gradients explicitly or anything like that. It's going to all be done for us. Okay, so we have our optimizer. Now, before we can actually start running training, we first need to initialize the variables, which is what we did before. And we're also going to create this saver, which will allow us to save the neural network weights as we go along. And this is useful since once you do training, you might want to use the model later. So this will save files that will help you do this. perfect. Thank you. But I would say it doesn't matter too much, or just try both, because it doesn't honestly take too much more effort to do the other one. Yeah, in back.
Please go back to where the opt variable was defined.
The opt. Yes, right here.
Yes.
So the optimizer can take in some values optionally. For example, you could pass in things like the learning rate. It depends on the optimizer, but for now we just use the default values because it's such a simple example.
Yeah, the order matters, the opt and the MSB.
No. So one thing to know is that within one session.run, everything is run at the same time. So basically you can view it as it's running the computation graph, so it's taking the input data and basically it's like water flowing through the graph, and all this passing in multiple values is saying is what pieces of it do I want to actually get back. So the order doesn't matter.
So after session, linked to back propagation.
After what?
After this session runs, linked to back propagation to access the values.
Correct. So what this is doing is it's taking the input batch, going all the way to the end, calculating the loss, that mean squared error, and that's the mean squared error you'll get. Then it's going to go back, do back prop, calculate the gradients, and update the parameters using the gradients. So doing one step of gradient descent.
So if I don't want any output, I can just put in an empty vector, and then it will still run through the graph.
If you don't want any, like if you don't want the mean squared error back,
For example, just nothing. Like I just want to run training, but not recording anything.
you need to pass in the opt.
I still need to pass the opt.
Yeah, otherwise it doesn't know to do gradient descent. Because the that operation opt is saying is do gradient descent.
But if I do opt right here, and then later on I do mean square error, it's okay. But I cannot do the other way.
I mean, you can split them up if you want. You could call sesh.run on opt, and then you could do another session.run on mean squared error.
So does it mean I train twice?
No. This is, I mean, basically, anytime you call session.run and you pass in opt, it will do one step of gradient descent.
Okay.
So to clarify, what the one called to Atom optimizer is doing is it's looking at which variables are in the computation, computing the gradient to optimize those variables.
Yes. So basically, by default, the Atom optimizer that you got here will, I'm going to scroll up, it will look at this list of tf.global variables, and it will say calculate the gradient with respect to all of the global variables and perform gradient descent on them. Now, let's say that you want to perform gradient descent on only some of the variables, like some of them are part of some other graph or whatever. You can explicitly pass this in. I just haven't shown that here.
Shouldn't you do, instead of for training step in range, something like while loss is bigger than something?
Yeah, you can do that as well, kind of have a stopping criterion, like keep training until your loss goes down. But that assumes kind of you know what the loss should be ahead of time.
But how then do you know how many steps?
So I'd say in general, you should be pessimistic about how long it'll take to train, but just print out as it goes along what the loss is, and then you'll get a sense for how long you need to train. Another option is that you can save, well, actually let me get to the next step, and I can also address that as well. So as you're running this session.run and you're optimizing, you're doing gradient descent, every so often it's probably useful to print what the actual loss is to make sure it's going down. And you can also save your model periodically. So one useful thing you could do is train for a long period of time, but save your model a bunch of times. And this will let you then look afterwards. You can say, oh, my loss was at the lowest right here. I should use that model checkpoint because it had the lowest loss, so it's going to be the best. So now let's say I go and I run all this code. OK, so it's running, and what's printing out here is what step it's on and what's the mean squared error. So as you can see, the mean squared error, the loss function is going down. Like, hooray, this is great. So it seems that training has gone well. Yeah.
So if you, since the opt depends input that, won't it still be available to you because it would be computed?
If you don't input which?
Like MSE into the sets.run?
Right, you don't need to input MSE to do gradient descent. You do not need to pass in the loss function. This is purely so that we can print it out so that you can see visually that it's actually doing well.
Okay, but the tensor value itself would not be available to you even though it's being used in the graph? Correct,
yeah. So TensorFlow, when I'm calling opt, will be computing a bunch of values behind the scenes. If you want any of those quantities explicitly, like you want to look at them, you'll need to put them, you'll need to add them to this list in session.run. Otherwise, it tries to do everything on the CPU or the GPU so that it runs as fast as possible.
For the server sections, for the every training step, you see what the CKPT file for that. So you just say one CKPT file, or you say a lot of CKPT.
So this one I actually was overwriting it, so it's only saving one. So I guess I couldn't go back before. TensorFlow does have functionality that lets you save multiple checkpoints. So I guess multiple of these as you go. So if you look at the API, you can see how to do that.
Is there a way to do something with overfitting?
Yeah, so one important note, I don't have a holdout set. So this is something that you might want to add. So to do that, you would need to do kind of the standard machine learning, take your training set, shuffle it, randomly split it. And then you could kind of evaluate the mean square loss, not just on your training data, but also on your holdout data. And this would be very similar to what you see here. OK, so we've trained our model. Now we actually want to use it. So we want to make predictions. So what we can do is we can, again, create our session. We can create the model, which is just creating the TensorFlow computation graph. So we get our input placeholders, our output placeholders, and our output predictions. And we want to actually restore the model. Since we're creating it from scratch, we need to go back to our saved model checkpoint and be able to load the variables it saved. So I create a saver, and I call saver.restore of that session, and I pass in the path to that checkpoint, which has all the variables from before. Now what we can do is we can say, OK, let's get the output predictions by feeding in all of the inputs. So by all of the inputs, I mean all of the x from here. So feed in just the x values, and let's see what the neural network predicts as the y values. And if we do that and we plot it, we can see that the neural network's predictions are in red, and the ground truth is in black. And hooray, it seems to have learned to match this sinusoid. One interesting thing you can see here is why are these very tight bends? This is because of the nonlinearities that we used. We used ReLUs, which have these lines and then this kind of elbow shape. And that's why you get that shape. So that's just something of interest. Are there any questions about kind of this simple regression problem?
Sometimes you need to write your own layers using the C++ and the CUDA. How to insert these layers to your model?
OK.
How to calculate the gradient?
Yeah, PU uses. But this is completely abstracted away, and there's almost, definitely in this class, you'll never, ever have to write C++ code. In my research, I've never had to do that myself. This is kind of a very special case. Basically, TensorFlow gives you the basic building blocks, basically the basic mathematical operators to do almost anything. So I understand your question. I guess for the purpose of this class, we will not be covering that, and that's actually even beyond my knowledge. That'd be for a class like CS294, like parallel computing. So yeah, I think that's outside the scope of this class.
It's support for complex number.
Yeah, can you say that again?
Complex number, it's all real numbers.
Complex numbers. That's a good point. I don't think it will work on complex numbers. Now you could let's say you know that your output should be a real number and a complex number, you could explicitly just predict 2 real numbers and do the complexes back together. But don't take my word on that. There might be some built-in functionality. Cool. Any other questions before I go into random tips and tricks? OK, now for random tips and tricks. The first one is really check your dimensions. So how do I do this? So let's say I created a constant that is of size 4 by 1. I create another size of 1 by 4. And as we saw before, if you multiply them together, you're going to get a 4 by 4, which is kind of weird when you do element-wise multiplication. So you should stop your code in the middle and like print out the raw tensors. It'll tell you the shapes and like really dig in there. Because if you don't, even if things do run, they might run but not work. Meaning that like it won't throw any exception, but it'll be incorrect. So really dig in there and stop your code. The next one is to check what variables you've created. So for example, if I create a variable A and a variable B, I can go through and print out every variable that I've created. So it says I am a variable and I am a variable too. And now this is useful since you might accidentally create twice as many variables. Maybe you have some loop and you did something weird. So this is kind of another sanity check. Make sure you know what you're optimizing for, what the variables are. The next one is actually, look at the TensorFlow API. You can either go on the internet or you can just open up a terminal and call help. So if I call help on reduce mean, it tells me, this is what it takes as input, this is what its output, and here's a few examples of calling reduce mean. So this is kind of how I interact with the with the TensorFlow API most easily. Another thing is that TensorFlow has some built-in layers that you can just use off the bat. So in the simple regression problem, we explicitly created all of the weights, all the biases. We did matrix multiplication, we added the bias, and we did the nonlinearity, and we did all of that manually. TensorFlow has some built-in things that will turn that, 10 lines into 1 line. And this can be useful to simplify things. Libraries like Keras also have kind of these functions that make things useful. They might even create the whole neural network in 1 line. But it's good to know kind of this 1D example where you do everything so you know what it's doing under the hood so that nothing surprising happens. Next, there's this thing called variable scope. Basically, you'll be creating a bunch of variables in order to train your model, and it can be useful to organize them so that you don't get clashes between different variables. So in our previous example, we created a 3-layer neural net. So we had weights W0, B0, W1, B1, and W2, B2. And to organize them, I can actually put them inside of a layer using this variable scope. So if I do this kind of with this tf.variable scope notation, and I go down and I print out the variables, you'll see that the names are actually preceded by what scope you're in. So basically, you can use this variable scope and nest it so that kind of you get some level of abstraction. There's kind of more nuances to variable scope, but that's something you can probably look up on your own. It's too much detail for now. Another thing is if you are using a GPU, which is not necessary, but it can make things faster. You can specify which GPU you want to use and what fraction of its memory that you want to use. I've left the code here. I won't walk through it, but just know that you can do that. This can be useful, so for example, if I want to use only half of a GPU, because then I can use the other half of the GPU to maybe try a different set of parameters. So it helps you iterate faster on your algorithms. And lastly, if you want to visualize things like the training loss, one approach is what I showed, which is where you just call session.run and you print it. TensorFlow has some built-in mechanisms for seeing what the training loss and what the holdout losses look like. It's called TensorBoard. Do I recommend using it? Maybe. It depends on you. I don't use it. Other people in our lab use it, so it's kind of up to you. So yeah, overall, this was kind of, basically the TensorFlow review session. Are there any last questions before we wrap things up? Okay, cool. So this notebook is already on Piazza. It'll be on the website along with the initial slides. And you should be good to go for homework 1. There's kind of not really any more knowledge you need for TensorFlow beyond this. But I encourage you to look at it yourself. Tons of tutorials online. Have at it. And you can ask those questions on Piazza and in office hours. Thank you.
Did you release the actual notebook?
Yeah, it's on Piazza. I'll repost it though. Yeah.
I was just wondering, I used the estimator page